Good afternoon. We did our final year project on the direct detection of optical power, which was supervised by Dr. Bill Corcoran. Our project aim was to create a directly modulated on-off keyed fiber optic link with components salvaged from legacy line cards with the possibility for future expansions. So now a bit of an introduction to the project. Direct modulation is the most simple form of modulation. This is because the hardware involved is very cheap. This is what makes it suitable for cost-sensitive applications such as fiber to the home and metro area networks. However, it is not suitable for long-haul links. This is because you would much rather use external modulation in this situation because it is much faster, however it is much more expensive. So now I'll talk about the background theory for a bit, starting with fiber optic cables. So the idea of using waveguides has been around for quite a while. However, the first fiber optic cables were developed in the 1970s. The thing is, at this point, they were impractical due to the high amount of attenuation, which is about 20 decibels per kilometer. Although the technology actually rapidly developed, and now the attenuation is much lower, which is approximately 0.2 decibels per kilometer. On top of that, technologies such as EDFAs and modulators and multiplexers also made optical communications much more viable. So on the right hand side, you can see a graph which shows the wavelength in nanometers versus the attenuation in an optical fiber. So at low wavelengths, you can see that there is a high amount of attenuation to what's called Rayleigh scattering, and on the right, you can see at high wavelengths there is a lot more attenuation due to something called infrared absorption. So you can also see that there are two windows at which we can transmit light at to have low amounts of attenuation. The first one is called the O band, which is at approximately 1330 nanometers, which has an attenuation of about 0.5 decibels per kilometer. And then you can also see at what's called the C band at about 1550 nanometers, you have about 0.2 decibels per kilometer, which is the best wavelength to transmit light at. So lasers are what's used to transmit light for an optical fiber, as opposed to LEDs. The reason why is LEDs use what's called spontaneous emission, where photons are excited up to higher energy levels, and at this point, after some period of time, they'll drop down and release a photon. A laser uses what's called stimulated emission, where just like spontaneous emission, the electrons are excited up to high energy levels, but what happens is a photon will come by, and that will cause the electron to drop down to the lower energy level, and what happens is the photon that gets produced as a result of the electron falling down is basically a copy of the original photon, so it will have the exact same energy, the exact same phase and direction, which is much more suitable for optical communications. So photodiodes are used as the receiver in an optical link. How they work is what happens is a photon will strike an atom on the photodiode, and that will cause an electron to be dislodged, which causes the current to flow through the circuit. Now there's two ways that you could wire up a photodiode, the first of which is called photovoltaic mode, which basically you have no bias across the photodiode, and what happens is based on the photoelectric effect, electrons will flow through the circuit. This is actually basically how a solar panel works. The other way that you can wire up a photodiode is in photoconductive mode, which is when you place it in reverse bias, which is the way that we've wired up the photodiode in our project. So when you directly modulate a laser, what you do is you adjust the injection current to the laser in order to turn it off and on. This is what's known as on-off keying. On the right hand side of this slide, you can see a graph that basically shows you a plot of the power of a laser versus the injection current. You can see that there's a point called the threshold current where the laser starts to turn on. And the thing is that basically the laser, it has a time at which the current can be adjusted. So what you want to do is when you modulate your laser and you turn it off, you only want to turn it off to the point of the threshold current, not to zero current, just so it doesn't take as long to turn the laser back on again. The other thing is that when you directly modulate a laser, one of the disadvantages that it has is it causes chirp at high frequencies, and what happens is chirp is basically when you turn a laser off and on directly, what happens is you introduce new frequency components, which is really bad for chromatic dispersion.
The fiber optic link consists of a transmitter and receiver capable of sending real data across a fiber optic network. A transmitter circuit is used to drive the laser. A constant voltage is supplied to the circuit, and a P-sock or a function generator is used to switch a transistor on and off, and hence drive the laser on and off, producing the modulation current. The laser laser used is a Philips CQF71, regulated by a 9V LM7809CV regulator. An 8 ohm resistor ensures the current remains below the laser maximum forward current. A BC456 NPN transistor is used to provide the modulation, driven by a P-SOC chip. There are 0.01 microfarad and 1 microfarad capacitors used to smooth any voltage fluctuations. The maximum laser switching speed is 300 megabaud. The emitted wavelength is 1515 nanometers. This operates in the C band, which means that it has a low attenuation per kilometer. Originally, we had a Philips CQF56 1330 nanometer laser, which would experience a much higher attenuation per kilometer. By plotting the output electrical power versus drive current, we can see that the threshold current for the laser to switch on is around 18 milliamps. The receiver circuit receives the transmitted signal using a photodiode in series with a low impedance resistor. An amplifier is used to amplify the voltage across the resistor to ensure it is at a readable level. The output of the amplifier is the intended data stream, which will be interpreted by a second P-SOC chip. The photodiode used is a 1 GHz photodiode, again regulated by the same 9V regulator. Amplification is done by a high-speed op-amp to ensure the amplification is possible at high data rates. The 27 and 680 ohm resistors provide a gain of approximately 27 for the non-inverting amplifier. Again, a 0.1 microfarad and 1 microfarad capacitor is used to smooth voltage fluctuations. Having a high R1 value leads to having a large time constant, causing long rise and fall times of the signal. Therefore, R1 needs to be small. However, having a small R1 leads to the output voltage being low, and therefore it needs to be amplified by a high-speed amplifier. Figure 12 shows a 50 Hz signal using a 100 kΩ resistor for R1. Here we can see the slow rise and fall times. P-SOC chips were used to provide the switching drive current for the transmitter and to receive the transmitter data stream. The inbuilt P-SOC UART module was used to modulate the laser at the transmitter. A second P-SOC at the receiver uses the UART module to connect to the PC, where termite serial communication displays the received data stream.
Now we're going to talk about the results for a bit. Firstly, we tested the link over a distance of approximately 5 meters. We were capable of sending a signal of 12.5 MHz using the oscilloscope, which is the maximum frequency of the oscilloscope. Using P-SOC, we were able to transmit data at a rate of 5 megabits per second, which is also the maximum data rate which the UART module is capable of. Here are two figures. The one on the left shows the waveform at the receiver at 12.5 MHz, and the one on the right shows the fast Fourier transform of what was at the receiver, also at 12.5 MHz. Note that what was sent at the input, at the laser, was also a square wave. So we've gone from this frequency at a square wave to a sine wave. One thing that we made was a form of one-way instant messenger. On the left-hand side, you can see the message that was sent using the transmitter. On the right-hand side, you can see the message that was received at the receiver. If you look closely on the right-hand side, there has been a bit error, which has caused a space to turn into a P. We did not do any form of bit error calculations because we also noticed that bit errors would occur when the two P-SOC chips are connected just by a wire. This made it impossible to see whether the bit errors were the result of the two circuits that we made. After we tested the system over a distance of 5 meters, we connected the transmitter and receiver units to the fiber optic link, which goes on a return trip from Clayton to Caulfield. Across this distance, we measured a total attenuation of 6.77 decibels, and we were able to send data across the link at a data rate of 2 megabits per second. Because of the attenuation, we had to modify the value of R1 so that the output voltage at the receiver was greater than 2 volts. This is because this is the voltage at which P-SOC distinguishes a 0 bit from a 1 bit. After we had tested the system over the Caulfield link, we attached two spools of fiber with lengths of 4 km and 14 km to the link. At this distance we achieved the same data rate with a total attenuation of 11.69 decibels. Now here is a quick video of our transmitter and receiver units connected to the Clayton Caulfield link. Now here is us sending data. here is a further analysis of the waveforms that we received. On the left-hand side, you can see a waveform that is 100 kHz and is essentially a square wave. Below it, you can see the Fourier transform of the signal, showing that there are lots of harmonics. The reason for the harmonics is because a square wave is a sum of multiple sine waves. On the right-hand side, you can see the signal at 6 MHz, and at this point, it pretty much looks like a sine wave. In addition, if you look at the Fourier transform below, you can see that there are much less harmonics due to the fact that the wave has lost its square shape. Now we'll talk about the limitations of the system and why we were not able to achieve the theoretical data rate of the laser. The first of the limitations which was imposed upon the system was the gain bandwidth product of the BC546 transistor, which was equal to 300 MHz. If you look at the waveform on the left, you can see that the output of the transistor at 1 kHz still looks like a square wave. But on the right, you can see that the waveform at 1 MHz no longer looks like a square wave, and it also never reaches 0 volts as it turns off. This means that at high frequencies, the laser does not output a square wave. The other factor which limited the system was the gain bandwidth product of the amplifier, which was equal to 300 MHz. If you look at the signal on the left at 1 MHz, the output of the amplifier still looks like a square wave. If you look at the signal in the middle at 6 MHz, you can see that the square wave has transformed into a sine wave. The thing is that the gain of the amplifier means that the maximum frequency of the amplifier without exceeding the gain bandwidth product is approximately 11 MHz. You would think that this would have no effect on a 6 MHz signal, however you can see that the shape of the graph has changed. This means that a square wave this is because a square wave will have harmonics, which have frequencies greater than 11 MHz which have been removed by the amplifier. On the right, you can see the output at 12.5 MHz, which has exceeded the gain bandwidth product of the amplifier. At this point, you can see that the amplitude is being reduced as the fundamental frequency is affected.
Due to the working and portable nature of the device, there are several real-world applications. The transmitter and receiver units can be used as part of a fibre-to-the-home link due to its relatively low cost. It is also possible to use the link in metro areas due to its 40-kilometre capabilities. Another possible use for the transmitter and receiver units is as an educational product. Students will be able to adjust parameters such as launch power, transmission distances, and fibre bend radius and observe how they affect the system. Varying the value of R1 resistor will give students an understanding of how the capacitance of a photodiode affects its speed.